Hello guys, in today's tutorial and a few other tutorials we're going to be looking at Proteus ISIS and Proteus errors. Now Proteus ISIS is what we use if we are doing schematic design, and that's what we're going to be looking at. And Proteus errors is what you use when you are doing PCB design. PCB is short for printed circuit boards. Now before you do a printed circuit board, you have to first do a schematic design and then transfer that to Proteus errors to create a circuit, if at all your project requires a circuit. Now in today's tutorial we're going to look at the basics of Proteus, how to find tools, how to navigate, all the basic workaround. So now I'm using Proteus version 8.6, but most of them are not so different. Okay, so when you first open Proteus, this is the home page that you're going to be looking at. So you can either click the new project button or go straight and click file, then new project. Alright, so in today's video we'll just look at the basics, and then later on we're going to look at how to how to design PCB design. Sorry, how to create a printed circuit board using Proteus. So for the project name, we can just call it basics, and then we can okay, I'm going to save this under my desktop. Okay, so inside Proteus, that's where I'll save it. Okay, so you can either start a new project or from a development board, but we don't have this. So okay. And then you can choose a template. This is just for presentation. If you choose default, then you don't have like the page layout and all that. So we can try with maybe we can try A4 landscape, or A4. We could just go for A3 landscape. Okay, yeah. So if you don't want to, you can opt out of creating a schematic, probably go straight to a PCB design, but starting with a schematic. So yeah, select that, then click next. And we are not creating a PCB layout, we don't need it at this time, so you can just stay with that option, and then yeah, that is basically it. So we can click next, and we are not doing a firmware project, because a firmware project would require us to select a microcontroller or microprocessor of some sort. So depending on what you have installed, if you have Arduino installed, you can always add these inside your well, you must have a you basically must have a package installed with various compiler for that. Okay, and I will look at these projects later on. So we are choosing no firmware project, then next, and just finish. So you should have something like that. You can zoom in and out. You can actually set author name and revision, maybe design title if you want to. File name is already set. So in order to do that, you go to design and edit design properties. This is it. Okay, so for the title you can just call it basics, and document number we can just call it 1 because it's the first one. revision, you can just say not applicable, and then for your author you can put your name, then okay. Right. So if you click, then the paper will refresh itself. Now my path is a little bit long, so it goes out of designated space, so there's nothing I can do about that. Yeah, there's nothing like go to a new line or something. Okay, so that is it for now. So we can, whatever we're going to design, we'll be putting the components here. Okay, yeah, so we'll be putting the components here, then we make a schematic design. So for that, there's component mode, there's a wire label mode. You can label the wires, text script mode, bus mode, sub-circuit mode, and terminal mode. But we're going to only cover a few of these. Okay, so this is for the instruments, measurement instruments. If you need to measure some signal, which is part of the circuit, signal coming from part of a circuit, and you can use one of these instruments. And we also have probe modes. These are also instruments, but no probes, like a voltage probe, current probe, and a tape. You know. So yeah, we also have there's a graph mode. You can add a graph that automatically draws the signal on a graph or plots a signal. Okay, yeah, so but we're only going to cover a few. So go back to component mode, and the P is for like place a component or something. So click the P, and we're going to look at just resistors. Just look at resistors, and then we try to measure like voltages across the resistors, and also look at the current through maybe the various branches, something like that. So for that, we'll be using generic resistors. So just type res. You don't have to finish the whole word, so just res is enough, and then look for resistor device, generic resistor. So you can choose this because you can easily set the value of resistance to whatever you want. Although there are others which are specific, but we are not going for these. These are actually diodes, but resistors, these are more specific. Okay, current suppressor, lead type, and then 10 ohms, then maximum current of 1.7, and the size. Okay, yeah, these are more specific. Resistance, these are more specific. Okay, this is 30.9 kilo ohm, and it has all the tolerances and whatnot, but we are just going for generic. Okay, then we need a power supply, so we need just type battery, and we are not choosing an active DC source. We're just using a battery multi-cell. So take this, and then we also need an AC source. This is for direct current, so we also need an AC source. So for that we use V sign mostly. Just like V sign. This is what you choose. What else we need? So the rest we are going to get from these other sections, especially for the instruments. Okay. So I'm going to just randomly make a circuit here, beginning with a DC circuit, so you can zoom in for better view. So just zoom in and Okay, I'm trying to center this, but okay, maybe that will do. So we need a battery and then some resistors. So first we can place a resistor here and another resistor here. Then we can rotate this clockwise. We just make a connection, simple connection. Just click at the end of the component and connect that wire. You can also click somewhere there for the joint and connect there. Okay, so the next thing is to run the simulation. Okay, maybe I should make this a bit smaller so that it can fit in this window. So the next thing to do is to run the simulation. If I run it, of course we're not going to see anything because we didn't set that we need to detect anything. So for that, I should maybe add some instruments. Okay, yeah, we don't need to use an oscilloscope because it's only good with alternating signals. For this, we are having a direct signal going through a resistor 1 and 2. So first, here maybe what we need is a voltmeter. It should be a DC voltmeter and maybe an AC. Sorry, a DC ammeter. So place an ammeter here. So click DC ammeter and place it here. Okay, something isn't right. Okay, I need to select that part first and then so that I'm allowed to choose this. Okay, I'll put it a little bit up here or maybe I'll just extend the battery to the left so that I can make a proper connection from here to here and from here to there. I'm going to add voltmeters across the resistors, so DC voltmeter, and then just place it here and one here. Then we can make this connection and also make this connection. Then we can rotate this whichever direction, doesn't matter, as long as we connect the positive to the positive, negative to that negative. So if I run the simulation once more, we should be able to get our voltages. Okay, yeah, so the current is 0 because the resistance is too high. Okay, it's too high compared to the voltage, so we basically don't have any current flowing through. Okay, it's like, yeah, well, everything is blocked from flowing, so it would almost register 0 current, although there's a little bit of current, but due to the precision of this, we can't detect the current flowing, and the voltages are rounded off to 4.5, which adds up to 9. So meaning there's nothing flowing. So if we lower the resistances a bit, we should be able to detect some current. So we can actually change this to maybe 300 ohms. Just double click the component to edit the values. And then we can change this to same 300 ohms. And we see if we can detect some current. So if we run the simulation again, okay, now we are able to see a change in the current. So we start to notice current flowing, but still the voltages are the same. Okay, voltage here is the same. So the sum of this and this should give you 9. Okay, and the voltages are equal since we have equal resistances. But we can change to, can make this 200, and if we run the simulation again, okay, so current is 0.1 and voltage across this is now 3.6, and this is bigger because of, the resistance is bigger. Okay, and so we can continually lower the resistances to see a change in current. So we set it to 100. We run the simulation again. Now current is 0.03 amps, and now voltages are 6 and 3. Okay, so we have something like that, right? So we can add another branch here, and also try to detect the current through the branches, okay, and see if it should add up to the current here. So if I stop this simulation, and I'm going to get rid of this wire, try to expand our diagram. So going back to component mode, make sure res is selected. I'll put a resistance somewhere here, and then I'll rotate it, move it somewhere here. So by all means, I'm going to have to extend this part. I'm going to move it this side, okay, then I'll move this bit here. Yeah, so now I think I'm ready to make a connection with component mode. Okay, maybe I should just start from here, make that connection, and then I want to add an ammeter here and here, and also well, the voltage should actually be the same, since these branches are in pair to the battery. They are in pair with each other, and then so they should have the same voltage basically. Maybe in order to be sure, we should add a voltmeter, okay, and see if there's a change. So going back to instruments, we need an ammeter, or it should be DC ammeter. So add it here, and we're going to rotate it, connect this to that, then we should add another somewhere there, rotate it, and we connect from here to there. Okay, so now what I'm going to do is to add a voltmeter from this point to that other point. Before that, let me make a connection here, here and there, then from here to the battery there. So DC voltmeter here, so that I connect this to okay, let me just put it there, and basically to that point, same as putting it here or there, it's still the same thing. So I'm going to change, maybe we'll leave it at 10 kilo ohms for now. If we run the simulation, okay, so this is what we get. We have 6.02, current here is still the same. So that shows that it's like we haven't done anything here. We've literally not done anything here. because the resistance here is too high, so that means mostly the current goes through the 100 ohm resistor. And this is 0.03 amps, and this is it's registering 0 amps. So we just want to make sure the sum of this and this is equal to this, of course, according to Kirchhoff's current law. So 0 and 0.03 should be equal to 0.03. So the voltages across here or here should be the same, meaning the ammeter, the ammeter doesn't have any resistance. That's basically what it means. It means it's an ideal ammeter. Of course, in reality, it's not ideal, but since this is a virtual kind of lab, then it's an ideal instrument. That is why there's no voltage change here. Okay, so we are going to change the resistance. We should make it smaller than 100. Let's make it 50. So 50, you don't have to put a symbol for ohms or anything, or R, because some parts are labeled with an R, but you don't have to put it, just put 50. If it's kilo, then you add a K, like that. So, okay. So if we run the simulation again, and now we are registering as 0.02 and this is 0.01, but still the sum should be this, okay? Yeah, that is the current that we are getting from this, okay? Yeah, so now let's try to, again, the voltage is across, there's a voltage change here, okay? There's a voltage change now because of the difference in currents, okay? So yeah, there's been a difference in current, so obviously there will be a voltage change, okay? Yeah, but still this sum of this and this should give us the 9 volt. So let's try to change this and we see what we get. Let's change it to 100 ohms. Then we run the simulation. Okay. Yeah, so if we run the simulation, now we are allowing in more current to go through, and the voltage has to be the same. Sum of this voltage and this voltage must equal to 9 volts. Okay, and yeah, still have more current on this branch than in this branch. Yeah. So let's lower the 100 down to 25. So we are allowing in more current with each reduction in resistance. So now it's up to 0.15. Okay. Yeah, and then voltage is highest this section. Okay. Yeah, because actually in order to determine the voltage across this, we need to consider the equivalent resistance in of the two branches. Okay. Need to look at the equivalent resistance. So equivalent resistance is definitely high, and then the voltage is high. Okay. The equivalent resistance here should be higher than 25 in order for us to have a higher voltage. Okay. Yeah, but current in this branch is highest, and then it's split at this junction to get this and that. So we are assuming the voltmeter has a very high impedance so that there's no current flowing through, and then we are assuming the ammeter is ideal, so it has 0 impedance, so there's no resistance at all, so all current goes through. Alright, so we can leave that and then look at an AC circuit. Yeah, alright, so in the next video we're going to look at an AC circuit, and we're still using resistors. So we're going to look at how to create an AC circuit and then try to measure the voltages across the resistors and the amps within the circuit. Okay, and then also add an oscilloscope then as an instrument, and then we try to measure things like the frequency of oscillation and possibly the peak to peak voltage. Okay, so see you soon in the next video. Thank you.